In this video, I will present the mathematical models that go with rotational dynamics and static equilibrium. So first we have the center of mass. This looks like a nasty equation. It's not that bad. So x for center of mass, so this is the x position of the center of mass. It is, if something is made up of a bunch of different pieces of mass, it's the mass of the first piece times the position of the first piece plus the mass of the second piece times the position of the second piece plus add however many pieces you've got, divide by the total mass of everything. That will tell you the center of mass position. For static equilibrium, I already said the net force is equal to 0. Also, net torque is equal to 0. Torque. Torque is R, so this is the distance from the pivot point. So distance from the pivot point times the force that's applied times the sine of the angle between R and F. So for example, this is a situation where there's a pivot point here, and then at some position out here, a distance R from the pivot, you apply a force that way. This would be the angle theta, the angle between R and F. Angular momentum. Just like linear momentum was conserved, final momentum equals initial momentum, same thing. Final angular momentum equals initial angular momentum as long as there is no external torque. And also, just like last time, we have a linear version and angular version, same things. F equals ma, right? We said that torque is the angular version of force. So torque equals m gets replaced by I, a gets replaced by alpha. So this is the angular version of F equals ma. Momentum equals mass times velocity. Angular momentum equals moment of inertia times angular velocity. For a point mass, that's a special case. That point mass, the angular momentum of a point mass is m times v times r, where this r is the lever arm. The lever arm is the shortest distance between, in this case, the velocity and the pivot. So in this case, if this is the pivot point, and there is some mass m that's going along with the velocity v, r is the shortest distance between the pivot and that velocity v vector. For work, work is force times change in position times cos theta. Here, work is force changes to torque and position changes to angular position. So tau times delta theta. There's no additional cosine component here as long as you maintain two-dimensional rotation and don't try three-dimensional rotation. We're not going to touch three-dimensional rotation. Now, one thing that's important to note, this theta here was the angle between force and displacement. This is a very different theta. It is not an angle between torque and something else. This is the angular displacement. Also, then we have power. Power was force times velocity times cosine of theta. Now, power is torque times angular velocity. And again, as long as we stay in two dimensions, we don't need to worry about the cosines.